Open an account for GPT 5.5 or Claude 4.7, and you are greeted with the exact same consumer starting point, a $20 a month subscription plan. Identical pricing masks a deeper engineering reality. These two models represent entirely divergent paths in artificial intelligence architecture, built to solve distinctly different problems. Aggregate benchmark scores suggest near parity, but in live automated production environments, they exhibit highly opposed behaviors. Success requires matching architectural profiles to precise execution environments. To deploy effectively, we must evaluate four operational constraints: multi-file reasoning, token economics, error handling, and cross-platform navigation. Relying on a standard win rate graphic obscures the mechanics of how these models actually function in the wild. We have to look at the execution data. The first environment test dictates how these systems manage software development and codebase infrastructure. Claude 4.7 retains persistent file system memory. When you ask it to execute a complex refactor, it maps the ripple effects across a sprawling dependency graph, tracking how a single variable change impacts 5 other files simultaneously. This chart-tracking SW bench verified data proves the advantage. Tasked with real-world GitHub issues, Claude resolves nearly 89% of complex problems, cleanly beating GPT's 84% by navigating cross-file logic like a senior engineer. Drop the environment down to a single file script or a command line interface, and the performance profile flips. This is GPT 5.5's native territory. Looking at the terminal bench data for DevOps operations, GPT 5.5 clears 82.7% of system administration tasks. It crushes Claude's 69.4% in tightly scoped, rapid execution tasks. The operational rule is clear: assign Claude to state-dependent architectural engineering and allocate GPT to scoped, rapid terminal commands. Once you move out of development and lock these models into an automated loop, coding capabilities take a back seat to unit economics. Claude's architectural thoroughness, its tendency to explain its logic and account for edge cases, creates a severe financial liability. Its outputs are incredibly verbose. This bar chart comparing equivalent API tasks reveals the core discrepancy. Even with identical inputs, GPT 5.5 uses up to 72% fewer output tokens to complete the exact same task. Run that efficiency gap across thousands of autonomous actions in a monthly billing cycle, and a $500 GPT workload scales to over $1,000 on Claude's infrastructure. For massive, tightly scoped API volume, GPT 5.5 offers superior unit economics that Claude cannot match. Economics matter, but reliability determines whether an agent can be trusted without human oversight. We have to analyze how these systems behave when they hit a dead end. An AI model that confidently outputs false data and passes it downstream to a database without triggering a human verification step will poison a production environment. This AA omniscience benchmark visualization tracks how models handle unknown data. The top path shows GPT 5.5 hitting an unknown variable. Instead of stopping, it guesses, hallucinating an answer 86% of the time. GPT's architecture optimizes for execution confidence. It prioritizes keeping the workflow moving over halting a process to verify a missing fact. Claude 4.7 operates as a cautious objector. When it lacks information, it halts the workflow and asks for input, reducing its hallucination rate to 36%. You can use GPT for outputs that will be verified immediately, like code compilation or math. But for high-stakes, unverified workflows like medical or legal data, Claude is a strict requirement. Beyond processing logic, we have to look at how these systems physically interact with the external software stack. GPT 5.5 relies entirely on structured ecosystems. It uses discrete APIs, JSON, and specific plugin architectures to push and pull data from modern applications. Claude's computer use feature abandons rigid code selectors in favor of raw visual perception. It views the screen exactly the way a human operator does. The vision action loop executes in sequence. It takes a screenshot, reasons about the visual layout, maps the coordinates of the target UI element, and physically moves the virtual cursor to execute the click. This grants the agent the ability to autonomously extract data from flat PDFs, navigate legacy desktop applications, and fill out unstructured forms entirely through graphical interfaces. The vision action loop solves the cross-application navigation problem for legacy enterprise software that APIs simply cannot touch. Giving an AI system direct system-level control of a mouse and keyboard immediately creates a critical new attack surface. Security engineers define this threat as visual prompt injection. A malicious actor can hide textual instructions inside an image, a web page, or an email. When the agent takes its screenshot, its visual perception layer reads those hidden pixels as system commands. If the agent executes those peripheral actions on a local, unsecured machine, the system is compromised instantly. Any GUI-based agent must be air-gapped. You run these models inside strict, isolated virtual machines to prevent unauthorized system hijackings. The deployment map is highly defined. Deploy GPT 5.5 strictly for high-volume API execution and rapid terminal scripting. Deploy Claude 4.7 for GUI navigation, multi-file refactoring, and high-stakes workflows. The Model Context Protocol now bridges this dual architecture, securely connecting both models to enterprise infrastructure. The future of engineering is no longer managing the AI models themselves. It is securely orchestrating the specific tools and environments they control.